Okay, well, it's my pleasure to introduce Steven Rayan, who's going to tell us about integrability and symplectic duality for generalized hyperpolygons. Thank you.
Thanks, Jack. Thank you and all the organizers for this really nice invitation. Of course, it would have been nice to travel in person for this, but you know, one day we'll be able to meet, you know, as a group once again. And you know, I'll reminisce in a similar way to Ruxandra that, you know, I was at Mathematical Congress of the Americas in Montreal 4 years ago, where I gave a very preliminary version of what I'm talking about now, which is now, you know, well, done and recently published. Well, done, leading to new open threads as always. But it's just nice that you know, somehow the MCA is sort of bookending you know, this project. And also thank you know, Ruxandra and Ronald and also Claudio from last week. You know, they've introduced a lot of terminology that I'm going to rely upon in this talk. You know, there's a connection here to Higgs bundles, even though it's not in the title, but it's nice that I can you know, refer back to some of the things that they've said. And this title, as you see, is slightly different from the one that I submitted with my abstract. It's there's just a bit more I want to say now in this talk than I had mentioned in the abstract. Let me say that this is joint work with Laura Shaposnik. It's the archive reference. It also appears now in Quarterly Journal of Mathematics. This also, you know, goes back to work I've done with Jonathan Fisher prior to working with Laura. So I want to set the stage by talking about talking briefly about what is called symplectic duality. This is a form of mirror symmetry. It originates in physics in so-called 3D mirror symmetry, but it's sort of become a subject in and of itself. And it's become a duality now between, you know, some, if you like, arbitrary symplectic varieties with some additional structure. So this is, we'll call these two spaces in the duality X and X with an exclamation mark. I'll call it X mark for lack of better expression. And these are typically referred to as the Higgs branch and the Coulomb branch, this terminology that you probably have all heard, even if you're not quite familiar with what they mean. And that's partly because, that may be in part because, you know, the definitions of these two objects are in some sense a moving target. As the notion of symplectic duality gets refined, the definitions of these objects are being refined in response, especially the Coulomb branch, perhaps the more mysterious of the two. I said that this is a duality of symplectic varieties, but one can really think of the basic ingredients here as being a complex reductive group G and some finite dimensional representation of that group. So the data here, you know, my Higgs branch X and my Coulomb branch X mark are these symplectic varieties, which are possibly singular, and which admit symplectic resolutions. I'll call them X tilde and X mark tilde. And we want these symplectic resolutions to carry actions of C star. And perhaps in its most basic form, symplectic duality is saying, you know, what it means for these two varieties to be symplectically dual is that there is a pairing in the middle cohomology, in the middle cohomology with regards to the C star equivariant cohomology of these two spaces, which admits a perfect pairing. And then furthermore, this induces a pairing with particular properties in the intersection cohomology of the singular varieties that we started with. This is perhaps the basic ask for symplectic duality, but it's become a much longer list of properties that intertwine these two varieties X and X mark, including, you know, duality of vertex functions, for instance, and various kinds of combinatorial properties that the two share. And I can't and won't be able to give you an exhaustive list of those But needless to say, I'm really just saying that there's something interesting brewing here at the border of symplectic duality, symplectic geometry, algebraic geometry, representation theory, and physics. Now you can ask, what are these spaces, or what should they be? Can X and X mark be anything, or can they be something, or are they something specific? Well, I think it's generally accepted now that X is a singular Nakajima quiver variety. And this quiver variety is cooked up from G and V in a particular way. The bigger question here is what is the Coulomb branch? And at least when the underlying graph, the underlying quiver of the quiver variety is of type ADE, as a Dinkin graph, if you like, then there's a recipe now for what the Coulomb branch should be, and this arises from BFN, Braverman-Finkelberg, Nakajima. And what we have here is an affine Grassmannian associated to G and to V. And one can think about this, since it's all about moduli spaces, one can think about this affine Grassmannian as a moduli space of V-framed G bundles on a formal punctured disk. And what one does is one takes a suitable homology of this moduli space, a Borel-Moore homology ring, and then one takes spec of that ring, which produces a variety. And this is, I guess, the best candidate for what X mark should be at the moment. And all of the properties of the duality that people are asking for are satisfied when X and X mark are these two types of spaces. Now, this definition of the Coulomb branch, I would say, is still good. For many more general graphs that one can pick to define a quiver variety, and instead of using just strictly ADE, you can have ADE-like graphs, which essentially captures all graphs that don't have, let's say, loops in them. I can try and decompose a given graph into A, D, and E type pieces that are connected together, and this seems to still hold. So this is quite a robust definition at the end of the day. And one of the things that's interesting is that this Coulomb branch comes with the structure of an integrable system. I'll say that both of these are hypercalar. At least the Nakajima side in a sort of maybe more obvious way. This tends to be hypercalar as well. I mean, this is defined using hypercalar reduction, which I'll talk about specifically how this is constructed in a moment. So you'll see the details there. And this is sort of there are examples where this is hypercalar, and it's expected to be hypercalar in general. And what this side has as well, it tends to always come with an integrable system, which is roughly speaking of Gelfand-Settlin type. So this is a complex reductive generalization of the integrable system that you get on partial flag varieties. So this is going to play a role in the story that I'm going to tell you as well. I mean, one can say that there's a sort of folklore belief that Nakajima quiver varieties should come with integrable systems. And this is giving us a clue as to what kinds of integral systems one should try to formalize on this side. And this story is really going to be about a particular Nakajima quiver variety, which is a so-called a moduli space of hyperpolygons. So this is a quiver variety for a particular shape of quiver. And I'm going to discuss integrability in the context of that particular Nakajima quiver variety. And then I'm going to speculate on the Coulomb branch in that particular case. But to make sure that we have the right equipment in place, I'm just going to review now briefly the construction of Nakajima quiver varieties. So last week there was a talk about quiver representations that's in the ordinary sense. Here I'm going to tell you how to sort of upgrade that to the Nakajima picture. So really, to get a feeling for this, I just have to give you, a couple of nodes and an arrow between them, and then everything else, is generalized from that. So, I'll have a couple of nodes that I'm going to label U and V, and these will come with weights, with dimensions associated to them. So this is part of the data of the graph. So I'm going to have some natural number here and some natural number here. Okay. And this arrow, the blue arrow here, is a map from CRU to CRV. So this tells me that I'm going to attach an RU dimensional vector space here, likewise RV dimensional here, and I just have a linear map from that vector space to that vector space. And I'll choose a basis, and these will be CRU and CRV. And you can work over an arbitrary field if you're if you want, although that will break down for us eventually, because we'll be going in a direction that mixes algebraic and symplectic geometry. But at least at the moment, this could be K. And so, if this were just an ordinary quiver, we would just be saying that rep of this piece of the quiver is exactly this Hom space. But in the Nakajima picture, you also have this backwards arrow. And this backwards arrow, you could say, well, that should be a map from CRV to CRU, and it is. But we don't want this backwards map to be independent of the representation you chose in the blue direction. We want this to depend on the choice that you made. So actually, this arrow lives in the cotangent space to Hom CRU CRV at the blue map that you chose. So if you like, so X here lives in Hom CRU CRV. Y, formally, is in CRV CRU, but that's after I apply the trace pairing to this cotangent space. But you should view Y as being in the cotangent space to Hom CRU CRV at X. And then you can view it as a map in the opposite direction by applying the natural pairing. Okay. So in any case, we have forward directions and backward is cotangent directions. And that's what we mean by a Nakajima representation. And I can just build this node by node, arrow by arrow. Now to a quiver Q, you can associate two special functions, which are moment maps. Okay, so we have the so-called real moment map, mu, which goes from T star of rep Q to the dual of a Lie algebra, which will be sum of, for each node, sum of URV of that dimension. And nu will be the complex valued moment map, which means that the sum of the Lie algebras is in GL. And I can build these moment maps node by node. So just to illustrate with a kind of graphical calculus, so let's take this picture here, and I want to build the contribution to the image of the moment map coming from the node U. So the way this goes is, I go out on X and then back on its conjugate transpose, and that's now an RU by RU matrix. And for Y, I do the opposite. I go out on the conjugate transpose and then back to the node that I'm interested in, and I take that difference. And that gives me something that is Hermitian. So it's not actually skew Hermitian. So this is a bit of a abuse of notation right here, but I could just multiply this by an imaginary factor. I'm just not going to do that because it doesn't really change anything for us. But just keep in mind that this doesn't technically live exactly here. And then the complex valued moment map, the component of its image originating from this node is you go out on X and back on Y, and now that's just GL valued. Okay. And again, you can just build these maps node by node. Now, what I want to do is take all of these Nakajima representations and mod out by an equivalence, conjugation action of the group G. So this is, if you like, change of basis operating on this. And this is just the product of general linear groups of the appropriate dimension for each node. And these act on the left and right of arrows as appropriate. You can make everything a left action if you want. But when we take this quotient, we're not going to get a nice moduli space of representation, so I have to impose a stability condition. What I'm going to do is what we call hypercalar reduction. And what I'm going to do is I'm going to choose my stability parameter alpha to be in the center of the Lie algebra of the group. Okay? And what I'm going to do is I'm going to take an intersection of level sets. I'm going to take the level set of the real moment map, add alpha, and then the 0 level set of the complex moment map, take this intersection and mod out by the group. And that's how I'm defining my quotient. So this is a generalization of symplectic reduction. And this is hypercalar, by the way, because it gets a complex structure from here, and if you like 2 from here, from the real and imaginary parts of the complex valued moment map. And then this is Hitchin, Carl-Heed, Lindstrom-Rocek hypercalar quotient. And this is, in fact, the Nakajima Quiver variety associated to the group G, or its complexification. So to take this, I should say, to take this quotient, I actually restrict it to the compact group and mod it out by plus or minus 1, which acts with stabilizer. So now G is compact, let's say, for all time. And so I'll say this is the Nakajima Quiver variety associated to the compactification, or the complexification rather, of G, and to representation V, which is in fact our T star rep Q. Okay, so I'll just give you a example, a really, if you like, a classical example here. So I'm going to take a so-called A-type quiver, and I have these all sort of strung out in a row. I'm going to have ascending labels here. I'm always going to start at 1, and I'm going to end at some R. And then in between, I have ascending labels, which ascending is the key property, okay? But I could be missing some, if you like. So this flag, if you like, is not necessarily complete. I could have all the numbers, or it could be missing some. Okay? And the number of nodes here is M. So M could be at most R if I have the complete flag. Okay. And you'll notice that I've used circles and boxes. Okay. So what that means is that I'm going to allow myself the freedom to not use every group, every GL group, or every unitary group rather, corresponding to every node to act. So I'm going to omit certain groups from acting. And so the circle and box notation is typically what's used in the representation theory and physics literature. So the circle groups are allowed to act, the box ones aren't. The box ones are the so-called framing nodes. Okay? So I'm going to allow them all to act except for the unitary group associated to the highest label here. Okay. And in this example, I'm using these play the role both of these are my dimensions. So here there's a U1 acting, here there's a UR2 acting, here there's a UR3 acting, and so on, but nothing is acting here. And then to take the hypercalar quotient, I need to pick something from the center of the Lie algebra, and I'm going to choose a real number corresponding to the Lie algebra here, and I'm going to let the rest of this be 0. Okay, so it's really just a real stability parameter. And when I take this, the quotient of T star rep Q of this quiver by this group here, then I get the cotangent bundle of a partial flag variety. So again, this is quite a common example. It's the A-type example. And this has some special properties. First of all, because I didn't use the group acting at the end, which is sort of important because if I allowed this to act, then that would kill all the moduli, and we wouldn't have a positive dimensional quotient. So it's essential that I didn't use this freedom here. But we do then have a residual UR action coming from this final node, and it has its own complex moment map, which is go out on Y, come back on X. Okay, I have subscripts here because remember this was the mth node. So this would be the m-1th x arrow. This is the m-1th y arrow. So go out on y, come back on x. That's a moment map for this residual action. And the image of this moment map is contained in the nilpotent cone, actually, of this Lie algebra GLRC. And this is due to the moment map conditions are all intertwined between the nodes, and they force this to be nilpotent. And when we have the complete flag, when we have everything from 1 to R, this map is actually the famous Springer resolution of SLRC. But in general, I'll be working with partial flag varieties. Okay, so this is really, if you like, some representation theoretic motivation for what we're looking at here. And what I want to do is, use this residual UR action to define a quiver variety. I just said that, if I use it, I'm going to kill all the moduli. So, one idea is to interlace some number of A-type quivers together with a common node labeled R at the center. And eventually that group UR is going to run out of steam. It's going to run out of you're going to use up that group acting on the first few of these quivers, and then you'll start to pick up moduli again. So what I mean is to look at a picture like this. So I have some flag here. I have superscripts 1 to say this is the first flag, and then the second flag, and then the nth flag here. So let's say there are n of these A-type arms. And they all have a common node in the center. And see, I've replaced this with a circular, it's a circular node. I'm going to allow the group to act. The idea is I have sufficiently many of these arms so that I get a positive dimensional moduli space. This is called a star-shaped quiver. It's the center arms of the star. Now since they're all circular nodes, I've taken off the circles. And I want to consider the even more general case where I have loops on the center. Okay? And that takes us a little bit out of the comfort zone of Higgs Coulomb branch theory, which is kind of what I want to do. And G is suggestive here, and you'll see why I call the number of loops G in a few slides. But yeah, this is referred to as a comet-shaped quiver because you could draw it like that. Okay, so there's all these sort of cute names: star-shaped, squid-shaped, comet-shaped. Okay? So there's a bit of zoology going on here. But so I want to consider these comet-shaped quivers, and I want to take their Nakajima quiver variety. Well, one of the fortunate things is that this, if I don't look at the center, this gave me a partial flag variety, or another cotangent bundle of a partial flag variety, and another cotangent bundle of a partial flag variety, and so on. So I can just, instead of reinvent the wheel, I have a product of those partial flag varieties, and then at the center, I have that these loops are self maps from R to R. So this is really in GLRC, in the algebra GLRC, but I'm going to actually restrict to an SUR action to make certain things simpler. So they're really in SLRC, and I'm going to double all of those arrows. So this is also going to have a T star here. So just have a product of these, which I'm now going to mod out by SUR acting at the center, using the complex moment map for that action at 0. Okay, you can ask where did the stability parameter go? It's hidden in each of these partial flag varieties. There's an alpha 1 here, and so on up to an alpha n, a real parameter for each of these partial flag varieties. But this is the Nakajima quiver variety associated to that comet-shaped quiver that I drew. And this is what we call hyperpolygon space, or generalized hyperpolygon space. So the original hyperpolygon space was studied by Kano, and also by Harada Proudfoot, and then by myself and others, and also Alicia Mandini and Leonor Godinho as well. But this generalized version of it is where you have the loops at the center. And so here's some notation to remember all the choices we made. So G loops, these are the dimension vectors of the arms, and this is the choice of the stability parameters, one for each arm. And you're wondering, well, what does this have to do with polygons? Well, you'll see that in a moment as well. But in the meantime, let me just say that this, when I take these stability parameters to be all 0, this is in fact the Higgs branch that we're dealing with in this talk. And when I choose a more generic value of alpha of the stability vector, that in fact is a symplectic resolution. In fact, it's a Crepin resolution of this this particular singular Higgs branch. So in fact, this is our x, and if you like, this is our x tilde from the very beginning when I was talking about symplectic duality. Now I want to demonstrate something about this quotient. So I just want to zoom in, if you like, on the center of the quiver. So I have some number of arms coming in. So here's the nearest node to the center on one of these arms, and then I have these loops. I'm going to call the loops, the blue part of the loops AJ, and then the doubled part BJ, to distinguish from X and Y's, which are on the arms. And I can simplify this this notation since I'm only looking at these arrows that are closest to the center. I can stop talking about m sub I, and I can just say that I'm just going to call these xi and yi without confusion. Yeah, there's a whole bunch of other arrows here, but I'm not really looking at those. So I'll just call these xi and yi to simplify the notation, and then I just have aj and bj. And if I write down the moment maps, if I write down the real moment map for the central node in terms of the x, y, a, and b data, it looks like this. So here's my going out on x, coming back on the conjugate, and then when you do this with the aj's and bj's, you get commutators of a with its aj with its conjugate, and same thing with the bj's. And I have n of these, n arms, I have g of these loops, and so that's what this expression looks like. And then for the complex value moment map at the center, I get a similar expression here. I have x and y's composed, and I have commutators of just a and b together now. And the 0 level set of the moment map is saying that I want both of these to be 0. Okay? But what we're if you stand back from this, this is happening in a particular Lie algebra, okay? in the Lie algebra, SUR, and this is happening in the Lie algebra SLR. And we're saying that there are 2n, so 2 terms here, summed n times. I have 2n vectors and 2 g vectors that are summing up to 0 in this vector space. This is some closed figure, and here I have n plus g vectors also forming a closed figure. And so the points in this moduli space are really polygons that look something like this. And so this part here is in the SUR part, and this part is in the SLRC part. So this is in the Lie algebra of a compact group, and this is in the complexification. And so this moduli space is a moduli space of pairs. And there's an analogy here between vector bundles and Higgs fields. There's a Higgs bundle-like story here, which I'm going to not go into too much detail about, but sort of hint at in a moment. But so this is really just to explain to you why one calls this hyperpolygon space. And by the way, if you don't look at the doubled arrows, the Nakajima arrows, that's the same thing as setting all of the y's and all of the b's to 0. And if you do that, this polygon here becomes smaller. You get rid of this part, and then it collapses together, just the x part and the a part. And this polygon completely goes away. And then you're just left with ordinary polygons in a vector space. So you get ordinary polygon space. Hyperpolygon space is when you have this sort of extra non-compact data, the y and the b direction. And you should think about this as, again, in terms of vector bundles and Higgs fields. Vector bundles are kind of compact objects, where the Higgs fields are the non-compact directions. But the main result here is that, remember, we did this reduction in stages. I had this product of cotangent bundles of partial flag varieties, and also this SLRC part tacked on from the loops. And we did reduction. This is actually a Poisson morphism. And this admits an integrable system of so-called Gelfand-Settlin type, and then you have the standard Lie-Poisson system here. And you can ask the question: do these descend to give you an integrable system, a completely integrable system on the hyperpolygon space? And under some mild assumptions, the answer is yes. If I assume that my arms are either complete, let's suppose I have C complete arms, and if they're not complete, then they're as short as possible. They go from 1 to R with nothing in between. So let's suppose that every arm is one or the other. Then you do get, you can at least, I'm not saying that in other cases it's not true, but in these cases you can see that the integrable system descends. And if I look at a complete arm, then I have various matrices, if you like, embedded in here, by looking at these sort of compositions of blue and red arrows that are on top of each other. And these have certain matrix invariants in them. So in a complete arm, each of these K by K blocks contributes K invariants to the story. And likewise, there are invariants that come from the minimal flags as well. If you do sort of a count of all the natural matrix invariants coming from the complete flags, you get this number here. And then from the minimal flags, you get a certain number, which is this. And from the Lie-Poisson structure on the loops, you also get a certain number of matrix coordinates, invariant matrix coordinates. And the sort of big part of the work here, which won't really have time to go into, is that Lauer-Shaposnik and I studied under the hyperkähler reduction, exactly what the reduction does to these matrices. And certain matrices are put into a fixed form or normal form. So there's a bit of sort of rolling up your sleeves and doing some interesting linear algebra under this hyperkähler quotient. And we sort of computed the number of invariants that get put into certain normal forms. And when you remove these from this total count, you get exactly half the dimension of the quotient space, of the hyperpolygon space. And these are all algebraically, and the ones that aren't put into this normal form are algebraically independent to begin with. And so you really do have the data of a completely integrable system here. And then in just the last sort of 3 minutes that I'll take for myself, so there's an integrable system here. It's of Gelfand-Settlin type, if you like, on this Nakajima Quiver, on this Higgs branch. And we said, we were saying at the beginning that Coulomb branches tend to have this type of integrable system. So this is somehow a very good sign. But I just want to also say that you can relate this now explicitly to Higgs bundles. It's sort of I've been advertising this a little bit as I've been going. You can relate this to Higgs bundles by taking, if you like, the hyperbolic plane, or if your number of loops is 0 or 1, you would take C, like Euclidean C instead. And you would tessellate the plane by a regular 4G gon. So this is Poincaré regular, if you like, in most of these cases, so for the hyperbolic plane. And also, you can also puncture, you can, say the fundamental cell of this tessellation n times, where n is the number of arms that the quiver had. So G is coming from the number of loops, and the number of punctures here is coming from the number of arms. And what you can do is you can write down a matrix valued function. So this is going to be the sum from I equals 1 to n of these compositions, these R by R SLRC matrices in that you get from the center of your quiver. So whatever representation you had, you take these R by R matrices, you get one for each arm. You put them here, and in the denominator you have your coordinate z in the plane minus zi, but on zi you're going to have a sufficiently periodic function, an automorphic form, if you like, that moves zi to the cell in which your coordinate z happens to be. So this would be the identity in here, but depending on how many cells you go over, this function is translating in a non-commutative way your punctures here through the tessellation. And then there's differential here. So this is a matrix value differential, and this is exactly a Higgs field for a trivial rank R bundle on the quotient of your hyperbolic plane by the Fuchsian group of this tessellation. And on an elliptic curve, if the genus is 1, or in P1 if the genus is 0. So there's there you go. G is suggestive. It stood for genus all along. But the point is that if I have a representation of a comet-shaped quiver, then I can cook up a Higgs field, and that gives me a map into a modular space of meromorphic Higgs bundles. They have poles. You can also get parabolic data, parabolic weights from the from your stability parameters alpha, but I won't go into that. Let's just say you get some meromorphic Higgs bundles on a genus G curve with n punctures. And so in that context, our result is saying that you have sub-integrable systems in meromorphic Hitchin systems that don't really come from the complex geometry of the algebraic curve. It doesn't depend on the complex structure on your quotient curve H mod gamma. It really just depends on the group data. So this is interesting. So we've identified, if you like, a host of integrable systems that depend on this representation theoretic data in Hitchin systems. And then I'll just sort of close by saying a couple of things. One, I wanted to connect to Claudio's talk from last week, where he was talking about this toy model on P1 with 4 punctures. So that's this quiver with no loops, and this will be rank 2 Higgs bundles, and all of the arms are as short as possible. And here you get a quiver. The hyperpolygon space embeds in the modular space that Claudio was talking about, and what it does is it misses the so-called Hitchin section. It gives you a different hyperkähler metric, which is just on the complement of the Hitchin section, and a different integrable system. And then the last thing I'll say is about symplectic duality. So it's a bit of a conjecture. So we said that one wants to look at affine Grassmannians in the construction of the Coulomb branch, and that's a moduli space of principal G bundles on a formal punctured disk, which is a lot like P1. Okay. So what this is suggesting is that for this case of loops, what one wants to do is consider a moduli space of V-framed G bundles, not on punctured disk, but on some K-to-1 cover of the punctured disk, where this K is tuned so that this in a formal arithmetic sense has genus G. So I really want to look at V-framed G bundles on a cover of say spec of the formal disk. And so this leads to a sort of conjectural Coulomb branch, which is spec of homology of a moduli space of appropriately framed bundles with appropriate sort of data at punctures of a sort of punctured branched cover of spec of the punctured disk. Or rather, spec of this Laurent series, which is the formal punctured disk, rather. So this is a way, if you like, of bringing genus into the picture, but it's inspired by this relationship between hyperpolygons, Hitchin systems, and the role of loops as genus, and that's where I'll stop. So thanks.
All right. Well, let's thank Steven. We don't have any time for questions, I'm afraid. So if you have any questions, please direct them directly to Steven. I guess maybe you can't private chat, but you can email or do anything like that.
Okay. Private chat seems to be enabled today, actually.
Oh, it is? Okay. Okay, yeah, good.
At least on my screen.
Okay. So we'll resume in 30 seconds or something. Aaron, do you want to try out your slides?
Yeah, let's see. Share screen. I'm going to stop Steven's sharing.
And are you okay if we record, Aaron?
Pardon me?
Are you okay